request Alex to, I forgot to ask her to push that up. Do we have a button here? Oh my God. Thank you, Mihai, and thank you, Alex, and thank you, Alex, for the. Okay, so I plan to write some stuff. So so thank you to the organizers for putting together this wonderful conference. It's really a pleasure to be back at ICMS after 8 years. And and to see lots of familiar faces and new faces and to learn about new math. It's very nice to be here. And yes, I will talk about Pólya frequency sequences and functions. So thanks to Anna and Projesh, I can speed up in the first part, since you've seen that a bunch of times now. So let's see. So again, so we start the conventional way. A rectangular matrix is totally positive if all the square submatrices have positive determinants, and totally non-negative if those determinants are non-negative. So in particular, all the entries are either positive or non-negative. So everything is real, no complex entries, all 2 by 2 minors and so on. These occur everywhere in mathematics. So they started out maybe more classically with analysis and matrix theory with Fekete and Pólya and so on. But probability in statistics has a lot of total positivity in it. In fact, Carlin has written this huge book, which was part 1, and he was supposed to write part 2 with the actual applications to probability in statistics. It never materialized, unfortunately. Of course, Schoenberg started this whole theory of splines, starting from Pólya frequency functions and total positivity. We saw talks on the first day yesterday, I guess, on about analysis, and so on and so forth. One of the original motivations was, of course, particle systems, in the book that's now translated in English. And then the other big push these days in total positivity is on the algebraic side, where Lustig generalized the notion of totally positive elements from type A, or what we know as totally positive matrices, to other reductive groups, to all types. And then Postnikov, Lamb, and many others have been working on the totally non-negative Grassmannian, cluster algebras, and so on and so forth. So lots and lots of work in many different directions in mathematics. So, okay, let me start then with the examples that you saw. I will not prove anything among these. So the first was, of course, generalized van der Waals matrices. And as far as I remember, it was Gantmacher and Krein in 1937 in their paper, provided the proof using Descartes' rule of signs. So, and then that example is used to prove, to provide one proof of Polya's lemma, that the Gaussian kernel is a totally positive. Well, now it's not a matrix. It is a uncountable cross uncountable matrix, if you will, R cross R. So given any real numbers index in the rows and real numbers index in the columns, you get a positive determinant. Here is one example that Projesh didn't mention, and this is simply the example where you write down ones on the diagonal and ones below it, and zeros above. This matrix is also totally non-negative. And I mention it because it will be, of course, important in what comes in. Of course, if you take a totally non-negative matrix, you take a submatrix, then of course, submatrix, so square submatrices are still square submatrices, so they are totally non-negative. If you take a limit of matrices, then determinant is a continuous function, so it commutes with limits. And so these things also preserve total non-negative. And the final thing that to build new examples from old ones is you multiply two such matrices, you get another such matrix, just because of the Cauchy-Binet formula. Right? So, okay, I will mention the Cauchy-Binet formula later again. But yeah, maybe I can write it out here. So if you have AB, this is M cross N, this is N cross P, and I want to look at the I cross J determinant. I indexes the rows of A, J indexes the columns of B. Okay? Then what do you do? Well, you can say that this is by Cauchy-Binet. This is equal to summation, maybe I'll call it I. Okay. So then this is, and both of these have size, let's say R. then all you do is you choose J from the set of n many common rows and columns. You choose a R element set of size, an R element subset of the rows and columns, and just literally write down that I cross J, that J cross. This is the Cauchy-Binet formula. Now, if A and B are both positive, totally positive, then these minors are both positive. So their product is positive. Summing up gives positive. So every minor here is positive. And the same thing for non-negative. So that's why products, the usual products, not Hadamard products, usual products of such matrices are in the same class. When I get to Pólya frequency functions, I will say that this is a discrete phenomenon and it has a continuous version. And that's how you will produce new Pólya frequency functions out of old ones, using the continuous analog of products. Okay, so we will get there. Now, a real sequence is a Pólya frequency sequence, as Pradesh and Anand already told us. If this semi-infinite Toeplitz matrix is totally non-negative. So, and then there are these two remarkable results. So I will sort of expand on what she told us the final answer, and I will expand on it to get there. Say that these finite one-sided Pólya frequency sequences. So what does one-sided mean? One-sided means that, say, it's lower triangular. All these entries are zeros. So that's one-sided Pólya frequency sequence. These are all built out of sort of some atoms by combining them in certain ways. And the certain way is just simply the product. And so let me tell you why. And that's, Rajesh, I think, mentioned this already, but I want to write this calculation up because I find it truly this miracle part. So suppose I define the generating function of a Pólya frequency sequence to be the power series that I get. It's one-sided, so I get a power series, not a Laurent series. If A and B are one-sided sequences, then they are, so now this means that these matrices are totally non-negative. So by Cauchy-Binet, the product is totally non-negative. The product is also remarkably Toeplitz. So that was sort of, I don't know why. Maybe somebody can explain to me why this should not be a miracle. But I'm just surprised. I mean, I can calculate and find out its Toeplitz, but I can't internally see it. This is very sort of annoying to me, if you will. Fine. But so it's a Toeplitz matrix. So you can ask, what is its generating function? Right? So, but let's first multiply this. Assuming that it's a Toeplitz matrix, the diagonal entries we all know, it's A0, B0. Everything above is 0. This entry here is you can just multiply, you get A1, B0 plus A0, B1. And similarly, you can check here, it's the same thing. And then this one, you can guess what it is. So this is going to be A2, B0 plus A1, B1 plus A0, B2. And the same entry here. So this is clearly, basically, this is discrete convolution, right? We are sort of convolving the sequence of A's with the sequence of B's. Fine. So now, on the one hand, you have this product. On the other hand, that's sort of the other miracle, is if you look at the generating function of this guy, then this is this number A0, B0 plus A0, B1x plus A1, B0x and so on. And the sort of miracle is that this is exactly as I said there. It's literally the product of this guy here times this guy. Which means that if you look at, if you look at the map taking TA and TB, sorry, TA and TB, you map it first to psi of A of x and then psi B of x, and then you multiply here, or you first multiply here, TA times TB, and then you take the psi function, you get the same answer. The map completes, right? So this is an algebra map. It's not just, it's clearly additive. The map taking T to psi is clearly additive, but it's also multiplicative. And so this is a very, again, I can see why this is true, and it's based on miracle one, if you will, but it's still an amazing property to have that. There are two different ways in which a one-sided sequence can be built into objects that can be multiplied. One is square matrices and one is power series. And the multiplications are exactly the same. Right? And I'll denote this map by script L for an obvious reason, or a reason which will become obvious later. Yes.
I think it's the Z transform, right?
Yeah, so that's the miracle. So maybe if I say understand the proof of that on the discrete level, then I should understand.
I would call it a Cauchy product because it's just the two lower triangle matrices
Right.
encode the Cauchy product.
It's called the Cauchy product.
If you work out psi A times psi D
Yeah.
elementarily,
Yes.
and you sort for coefficients, get exactly
You
that.
get those. But yeah, I understand why the coefficients are on the lower level of these. I just don't know why I can see them here. The diagonal entry shirts. Diagonal entries are products, but then now I know that it's this times this. Of course, I know that how you multiply matrices. But is there a conceptual reason why this is the
Your
thing?
nilpotent matrices are
Because it's a
behaving.
triangle summation.
Sorry?
Your nilpotent matrices are behaving like the appropriate powers of X.
Okay. But do you exactly get, okay, maybe you can explain it to me afterwards. Okay, thank you. Alex will tell me why.
They come from Hardy space. So you have Hardy space, multiplication, and it explains everything.
Okay, so now I don't want to go to Hardy space to understand matrix multiplication,
But
but
you can do it algebraically.
you can do it, yeah, as long as. So now you see where the miracles come in. Hardy space, powers, nilpotent matrices. No, there is a lot going on in here. Okay, fine. So either way, miracle or not, hence I put the question mark. You are free to remove strike it out. I put the question mark. Okay, so that's why products, fine. So products means that I can now forget about writing an infinite matrices. I can just look at the power series downstairs. And from these, I can tell you, we can get new Pólya frequency sequences, just looking at the power series, not the infinite matrices. So as I said, for me, this is easier to look at than that because I understand multiplication here. Fine. So these are the two sequences that we saw already in the previous talk. One is, or maybe I think, so the first sequence is literally just A naught at one place, which means it's one diagonal. It's a diagonal infinite matrix. I claim this is totally non-negative, and that's because if you choose whatever many rows and whatever many columns, let's make them appear differently. You either get a row of zeros or a column of zeros, or it has to be a diagonal matrix. And A naught being positive or non-negative, the determinant is fine, positive. So this is totally non-negative matrix. And similarly, the other one is where you have A naughts, and then you have 1 and alpha. So alpha is below. And now so either again, you choose a submatrix, you either have a row of zeros or a column of zeros. The only non-trivial cases are when you choose a matrix where you get something like this. Alpha's on the diagonal, 1 above it. Or you get something like this, 1's on the diagonal and alpha below it. So you can get two different types of triangular matrices. And so I did not say lower or upper triangular. Anyway, so these are all, again, the determinants are non-negative. So indeed, this is still in here. So here are two basic building blocks. And now we know how to build new Pólya frequency sequences from old ones. Just multiply them up. And so once you do that, this atom is, the generating series is 1 plus alpha x. So therefore, this generates a Pólya frequency sequence. And as Prajesh said, this is all of them. Right? They are all of them. Why are they all of them? Yeah, so that's the hard part. But we got all of them. The hard part is to prove there are no more. One of the easier proofs was, so one way was done in this paper that Anna mentioned, where they classified all one-sided sequences. They don't stop here, they keep going. As a special case, you get the classification of the finite ones. An easier, maybe a more accessible way without using hard complex analysis was found by Schoenberg in the 1955 paper, which Prajesh referred to. And that just uses matrix theory and basic complex analysis to understand why 1 and 2 are equivalent. Yeah, so the roots are obviously negative. It's negative alpha I inverse. So those are negative numbers. The claim is that this is also equivalent to the generating function having m real roots. You don't need to specify that they are negative. They are real. Well, obviously, if they're real, they're negative. Sorry, if they're negative, then they're real. So one way is obvious. But if I know that this is M real roots, then why are all of them negative? And that again goes back to the 1600s and Descartes' rule of signs. And so how many sign changes are there when one writes out this polynomial?
We do not need Descartes.
You don't need Descartes. Okay.
If coefficients are positive, we can't have positive root. It
And
is not.
Is that easier without Descartes as well? Is it trivial?
Because in each positive value x,
Yes.
the sum is positive.
Ah, okay, you don't need Descartes. Yes. Please evaluate the
In this
polynomial. Yes.
situation.
In this situation. Yes. Evaluate the polynomial and check it doesn't vanish. Thank you, Anna. Yes, that's much easier than what I was thinking. So yeah, and it's not even at 0 because the constant term is positive. So 0 is not a root. Positive numbers aren't roots. If it has real roots, they have to be negative. Great. Okay. So this is the theorem that classifies all finite diagonal matrices which are totally non-negative. Matrices. What about the infinite ones, meaning infinitely many non-zero diagonals? There is only one other atom that one needs, and one needs the notion of limits. So here is the first atom, which is that this matrix that I started with, the matrix with all ones, I can make it infinite. There's no reason to keep it 4 by 4, 5 by 5, 7 by 7, infinite. So that matrix is a Pólya frequency sequence. What is the generating function? Precisely the geometric series. Fine. So yes, it's 1 plus x squared plus x cubed, so on. So the geometric. So that is Pólya frequency sequence or its generating function. The claim is that I can make any geometric series and still get a Pólya frequency sequence. And you will see, I just wrote down the proof because it's one line. And you will see this one line at least, I think, twice more in this talk. So the same proof again and again. If you look at the choose some rows and choose some columns, arbitrary rows and columns, look at the corresponding submatrix. That submatrix's entries are literally beta to the Lj minus Mk. So when you can write it down, it factorizes as a diagonal matrix times the ones matrix times the diagonal. So these are all non-negative determinants. So I hope that's clear. If you have questions, please, yeah. Or if you have easier proofs also, then please let me know. Yes. Yes. Okay. So yeah. Therefore, this now is a Pólya frequency sequence because the diagonals are 1 beta beta square. So that is the only extra ingredient you need beyond the basic ones that we wrote down here to recover all the possibly infinite one-sided Pólya frequency sequences, which Anna already told us what they are. And the other thing you need is limits. So if AM are Pólya frequency sequences, we know that totally non-negative matrices are closed under limits. So done. And the example that we already saw for Fekkete's example, I'm not saying it to repeat something that was said. I really need this particular thing. The exponential is a very special Pólya frequency sequence, as you will now see. So let's put all of this together. We already saw these guys. These are corresponding to this bidiagonal infinite matrix. Those are each individual factor is a Pólya frequency sequence. Products, so j equal to 1 to n, not infinity, 1 to n is still Pólya frequency because products, it generates one. And then now you take n goes to infinity. As long as the alpha j's are summable, this is less than e power alpha jx. So this is still convergent. So this is a Pólya frequency sequence. Similarly, so is the second factor. All the partial products are, and therefore the limit is. And now, as I said, this extra special Pólya frequency sequence is also at our disposal. Put all of these together. This is a power series, one-sided power series, which generates a Pólya frequency sequence for all the possible delta bigger equals 0 and summable alpha j and beta j non-negative. And the theorem, that was the theorem that we saw earlier. A one-sided sequence is a PF sequence if and only if it is of this form. Let's say, so you should put a constant factor here. That's why I just put a naught equal to 1 to normalize it. A naught should go here, if you will. And Anna had the extra term of x power m here. That is just shifting the diagonal to start from am rather than start from a0. So that's the x power. If you put an x power m here, it starts later. But you can always, it's infinite, so you can decide to offset it or not. And so one way, as we just proved one of the implications, each of these is a Pólya frequency sequence. The converse is very hard. It uses hard complex analysis. Yeah. Okay, so now what about, so let's look at these guys. Clearly they have poles. What if there were no poles? Then that function must be of this form, and this is what Anna already told us. So this is why I can go slightly faster in this part. Next to previous slide. This is the form, and it is yeah. This is the function that is entire, and yeah, is in fact, let me just say, let's write this one. This is a limit of polynomials. What polynomials? Let's say n goes to infinity, 1 plus delta over nx to the n. This is like alpha jx, similarly, times the product. A goes from 1 to n, 1 plus. This polynomial has all negative roots. And the limit is not just sort of, the limit is basically uniform convergence on compact of the complex plane. This converges on all of C, and convergence is uniform locally. Such functions, such entire functions, which are uniform limits of real rooted polynomials, are said to be in the Laguerre-Pólya class. This was a big industry at the turn of the 19th century. And shortly after, so that started with Laguerre's result, which he showed us, and then Pólya refined it. And then they connected the result to multiplier sequences. So in fact, an entire function like this generates a one-sided Pólya frequency sequence, if and only if it is of this form, as the previous theorem implies. That's called the first Laguerre-Pólya class. And that was proved by Pólya and Schur to be if and only if the terms n factorial times an form a multiplier sequence. An is the generating function of the Pólya frequency sequence. So multiplier sequence just says, yeah, that if you have a real rooted polynomial, then if you take the Schur product, right? This was called the Schur product, and that is also real rooted. Well, what is the journal?
Oh.
Yes, the journal. So, but the point is, this was, as I said, a very hot topic in the early 1900s. It is also remains a hot topic in this decade, 1 century later. And this has found, really like multiplier sequences in multiple dimensions now, and many other far-reaching generalizations by Borchea and Brandon in the 2000s decade, 2 decades ago. And what was taken forward the last decade in these 2 very, very famous papers that I think we all know about by Marcus, Spielman, and Srivastava. So this Laguerre-Pólya class really has had deep consequences in mathematics for quite a long time now. And we will see one more consequence. Actually, Karl-Heinz already told us one more consequence yesterday, but that's the dessert part of the talk. Let's go to the second course of the talk. So now we come to Pólya frequency functions. So as we saw earlier, the Gaussian kernel is strictly totally positive. I should point out that I will say totally non-negative and totally positive corresponds to yesterday's talk was totally positive and strictly totally positive. Actually, even Anna said that. So my notation is the same as what Projesh used, Tn and T. A function is totally non-negative, and I will differentiate from between Tn functions and Pólya frequency functions because they are slightly different for me, I guess. Well, they were also slightly different for Schoenberg, so I will cite Schoenberg. But yeah, such that the Toplitz's kernel is totally non-negative. That's basically the same idea that, here we have an array of numbers, A0, A1, A2 in a Pólya frequency sequence. That's a one-dimensional array serving a two-dimensional grid of entries in a matrix. This is a one parameter function, and it's going to become a 2-parameter kernel. That's the Toplitz's kernel. The same analogy. Examples, the Gaussian kernel, as we saw multiple times. This is the Dirac delta function. It's 0 everywhere except at one point. And the claim is that is also a totally non-negative function. And that's basically because if you look at its kernel, it looks basically like this. So of course, this is totally non-negative. Another one is the exponential. Any change of origin and scale, that's what it's called. So why again? Because, well, if you look at if you draw any submatrix from it, this is the entry. every entry is positive. So 1 cross 1 minors are fine. It's rank 1 because it's very clearly rank 1. So 2 cross 2 minors and bigger are 0. So it's totally non-negative. All minors are non-negative. And the fourth one, which is called the Heaviside function, which is basically 0 until some point and then 1 beyond that. And you can check. Basically, this corresponds again to this this kind of a matrix. The matrix with ones below the diagonal, zeros above the diagonal. So these are four very different examples, but all of them have the same property in common. They are totally non-negative functions. One is pathological, one is sort of weird, one is, well, maybe not weird. It's a nice function. I guess. But again, somehow this matrix again eludes me. Why this is, you have to do lots of case by case analysis for this. I looked at Carlin's book and he does case by case analysis as well. So I don't know of a conceptually nice reason why this is totally non-negative. But yeah, the last two examples, 3 and 4, are clearly not integrable. If A is positive or A is negative or A is 0, this function is not integrable. The last function isn't either. And this function is just pathological. So Pólya frequency functions are such functions, totally positive or totally non-negative functions, which avoid these two pathologies. Function is PF if it's integrable, first of all. It's non-zero at least at 2 points. It can't be a Dirac delta. And the associated Toeplitz kernel is totally non-negative, like in the previous slide. But these are really beautiful objects. That's why I wrote the footnotes. And they were developed by Schoenberg and later others. Carlin, again, of course, really went into this theory, this book. They connect to many different areas again. Here are some couple of consequences of the definition. The moment they are non-zero at 2 points and totally non-negative, I think you don't need part A either. Just parts B and C imply that they are non-zero either on half of the real line or on the full of the real line. All Pólya frequency functions are non-zero either on the semi-axis, this side or that side, or non-zero everywhere. And they are continuous except at most at 1 point. And even at that point, the left and right limits do exist. Almost, so it's just a matter of where the value at that point is. Is it here? Is it here? It can be anywhere in between the left limit and the right limit, but okay. So now let's look at examples of Pólya frequency functions. So the Gaussian kernel is clearly integrable, non-zero at least at 2 points. And as we have seen already, it is strictly totally positive. So function, so yeah. This guy was not integrable, but it satisfied the other two properties. So you can make it integrable. It's very easy. Multiply by exponential. Why does multiplying by exponential retain total positivity? Because again, when you multiply by an exponential and take xj and yk, you again have the same factorization, a diagonal on the left, a diagonal on the right.
So if you go back to your previous, so you
Yes.
can replace, if you've got the second two, B and C,
Yes,
and you can always multiply by an exponential to make it integral.
that's right. Okay, I don't think I put this on the slide, but every
That's in Sherman's.
that's of course, yeah. So I should put a third one here. Yes, every totally non-negative function. Thank you, Alex. A third consequence is every Tn function of the previous kind, as long as it satisfies B and C, you can multiply it by some exponential factor. Because even Karl-Heinz said that they have exponential. At least you or maybe others, that all these functions have exponential decay. So basically, if it's not integrable, but it satisfies B and C, and so total non-negativity, you can multiply by some exponential, either plus or minus, to make it a Pólya frequency function. And so basically the same kind of calculation would work in general there. And the determinant is non-negative. Fine. So that's another Pólya frequency function. So these are the two, this is called a two-sided Pólya frequency because it's non-zero on both sides. This is a one-sided. And now I have a function that looks like this, the standard exponential decaying function. So I have this, so this is my function. It's 0 everywhere here. Okay, I think people can't see over there. This is a Pólya frequency function. The point is, if this is a such a function, so is its reflection. So if you do this, this is also a Pólya frequency. So that's what I say in the next thing. If lambda is a PF function, so is any scalar multiple. Oh, sorry, this should be positive because the function better be non-zero at 2 points. But yeah, for c bigger than 0, as long as I don't, as long as a is either positive or negative, and you can move the point here. So it need not be here. The x-axis can be here, y-axis can be here. So these are what Schoenberg called change of origin, the B part, and scale, the A part. You can move the origin by B, you can shift and you can scale it up or down on both the input and the output sides. And again, limits of PF functions, so if they are non-zero and integrable, then they are PF functions. So basically this is saying limits of Tn functions are Tn. Total non-negativity is preserved under limits. Okay. So these are some ways of constructing new Pólya frequency functions out of old ones. You can change the origin, you can change the scale, you can take limits. And here is another way. So the first one was the matrix case, which we said. If you have two totally positive matrices, like over here, then their product gives you a new totally positive matrix or totally non-negative. And as we saw here, if you have, for example, Toeplitz matrices like this, then their product is really discrete convolution. When you multiply these matrices, we are really convolving them. And that is the correct notion that carries through to the continuous case. The Cauchy-Binet formula has a continuous version, as I said, due to Pólya and Szego. And this implies the following corollary, that if you have two, I don't know why I said integrable, they are Pólya frequencies, so I don't need to say integrable. If you have two PF functions, then their convolution is also Pólya frequency. And this is going to help construct additional examples of PF functions from old ones. So in the spirit of what I told you about atoms and products, now the atoms stay atoms. Every Pólya frequency function is going to be built out of atoms, but the product now becomes convolution. The product here was actually discrete convolution. That's what we will make continuous. So now for the name, so there was this isomorphic, this algebra map taking the Toeplitz matrix here, the generating function here. I called it L. And this is why I called it L, because that was basically called the discrete Laplace transform. And so the usual Laplace transform in the continuous setting is this, and this is an algebra map under convolution. And that is the continuous analog, or this is the discrete analog. By discrete convolution, with respect to that, you get an algebra homomorphism. So now let's look at these one-sided Pólya frequency functions, meaning they are 0 on some half of the real line and then positive. Let's just say positive on the infinity side and 0 that side. I could reflect it, but let me just stick to the positive side. Let's look at these guys. So basically all of these are the basic things, these are the basic examples that we saw here. This was the only one-sided example we saw here. In fact, we only saw 2 examples really. And then all others are like procedures to build more examples. These are the only 2 examples we saw. There's a reason these are the only 2 examples there are. So let's talk about it.
Why does L lambda exist for all S and C?
It doesn't, it's sorry,
Okay.
when defined, I should have said.
Okay.
And it exists in some vertical strip,
Okay, yeah.
the usual, yeah. Sorry, that, yeah. If converted, defined. But it is always defined on a strip containing the imaginary axis, because if S equal to 0, if S equal to 0, then the lambda is integrable. So therefore life is good. Okay, so now let's look at these. I'll define phi A to set some notation. A, of course, better not be 0 then. And this has, you can compute the Laplace transform, you get this particular thing. 1 over 1 plus AS. So let's again take some summable series, alpha AJ, which I think yesterday and even today you took 1 over xj. I'm putting it upstairs, so AJ. Then for each n, you can look at a finite convolution of such functions. And because Pólya frequency is closed under convolution, each of these is a one-sided Pólya frequency function. They stay one-sided. When you convolve, just like if you multiply 2 upper triangular matrices, they stay upper triangular. And if you convolve to one-sided functions, they stay one-sided. These are what we called Hirschman-Widder densities, Alex, Mihai, Dominic, and I, in our paper 2 years ago. But because we call them that because Hirschman and Widder wrote this book studying exactly Pólya frequency functions of finite type, as Barnheim's called it. So they wrote this book shortly after. No, it was before Schoenberg's published paper, I think, right? But it was after his PNAS announcement of that paper. So it was somewhere in between that they published their book. So yeah, so that's why we call it Hirschman-Widder densities. These have the Laplace transform, which is just a multiplication because of the algebra map. And as I think Joachim said yesterday, you can also write these either as convolutions or as linear combinations. And yeah, fine. One can now shift the origin. So this is basically, these are all 0 until the origin and positive after it. We can change the origin and scale, as I said, as Schoenberg said. So one shifts the scale. Once you shift the scale by something, the Laplace transform changes by this factor, exponential factor. Right. So now taking limits of these functions gives us a new Pólya frequency function whose Laplace transform is this guy. It's basically a Hirschman-Widder density shifted. Its reciprocal is exactly this. So we took the limit. So therefore now this is where harmonic analysis somehow works well in this setting. So limit commutes with this product and so on. Its reciprocal therefore gives you this function which we wrote down over here. This was the same thing that we got from Pólya frequency sequences. One-sided. And now we are getting it from Pólya frequency functions, also one-sided. This is the reciprocal of the Laplace transform of a certain function, which is Pólya frequency, because limits of Pólya frequency are still Pólya frequency. So finite convolutions is still in the same class, limits stays in the same class. And its Laplace's reciprocal is that. Theorem, there are no others. This is Schoenberg's first theorem, let's say. Class 1, a function continuous, say on this part. Okay, I think I forgot the delta part here. Anyway, and then an integrable integrating to 1. If it integrates to 1, then the value at 0 should be 1, and that's exactly true. If you put s equal to 0, you get 1. Is a one-sided PF function vanishing downstairs if and only if this happens. So that class, that thing is in the Laguerre-Pólya class. And as I said, this is the limit of these polynomials. And then similarly now, remember that there was one more. We used the exponential functions and we use limits. But there was one other atom, the Gaussian. And now you can use the Gaussian and you can use these guys which look this way, which are positive this way, and their reflections which are positive that way. And you can start convolving some of these things, and a Gaussian. And together with all of this, you get the form for a general Pólya frequency function, not just one-sided ones. And these are and you see exactly the same kind of terms that Anna wrote, minus quadratic plus linear, and then something like this. And then there is a condition on the level of convergence. So this is the Laguerre-Pólya class of type, or what's it called? The second Laguerre-Pólya class, the two-sided ones. Okay, so this is what it is. This was already said, so I don't need to spend too much time here. And again, this is the class of functions that then Borchea and Brandon and Marcus and Spielman, Srivastava, they took forward in many different ways 100 years later. But now, somebody, I don't know, was it Mihai who told me? Somebody told me that at that time, the Laguerre-Pólya class was a big rage, for among other things, to try and prove this, which we saw yesterday and I think today as well. Right? So the Riemann psi function is this thing. This is in the Laguerre-Pólya class if and only if the Riemann hypothesis holds. So combining with Schoenberg's result, this is what Karl-Heinz told us yesterday. If this sort of inverse Laplace transform or something is a Pólya frequency function, then you win $1 million. But sadly, this didn't happen. So fine. This is true on the Pólya frequency function side. But there is also the same phenomenon on the Pólya frequency sequence side. Because remember, I got the same thing here, Laguerre-Pólya class, from the sequence side as well. I got, meaning Schoenberg got it 70 years before. But yeah, so Olga Katkova, who will speak on Friday, unfortunately online, she can't make it. In this conference, she proved this thing 17 years ago, that again, if this generates a Pólya frequency sequence, if you look at the this entire function and you look at the Taylor coefficients, if they indeed generate, if they are a generating series, the psi for a Pólya frequency sequence, then again the Riemann hypothesis is true. And she proved that this is Pólya frequency, meaning if you look at the 43 cross 43 minors of this Toeplitz matrix, or 42 cross 42, or 35 cross 35, all of those are non-negative. But I don't know about 44 cross 44 minors. And then she proved that asymptotically, it is indeed true that for every size, these minors are non-negative, as long as in this totally non-negative matrix, you go sufficiently far below. Then you can look at 44 cross 44 minors, and this is non-negative. But you have to go sufficiently below. That's the problem. Oops, but it connects. This Pólya frequency sequences also lead you to the same class of entire functions, and therefore to a characterization of the Riemann, reformulation of the Riemann hypothesis. Yeah. Okay. But here is another reformulation of Pólya frequency themselves. So this is something that I learned much later than I should have. My major was in statistics, but sadly, nobody told me this fact. The word frequency in old times, in Schoenberg's time, for example, was used to denote histogram. You do frequency analysis, and that's where the word frequency comes from. So these were supposed to be exactly modeling probability densities, and once you normalize by the integral, they are. So traditionally, frequency functions are densities of PDFs, right? PDFs of random variables. The more interesting part is what happens under convolution. If you have the densities of two random variables and you convolve them, you are really looking at the density of x plus y, provided x and y are independent, let's say. So Schoenberg's theorems reformulate, and we wrote this up, put it somewhere, and say that the one-sided variant of Schoenberg is Pólya frequency functions vanishing here, positive here, are precisely the densities of positive real linear combinations of IID exponential random. And remember that these are Tn because why? Because multiplying by any exponential to the one function. So these functions are Tn because of the matrix there. And if you multiply a Tn function by something like this, exponentials just pre and post multiply by some diagonal matrices. So that was Tn's. That was easy to prove modulo that fact. So these are Tn, and now any Pólya frequency one-sided function is the probability density of a sum of these. And you can take a countable sum, finite or countable. Two-sided variant, you just need to add, you just need to allow some negative coefficients because of the reflections, and or add one more normal variable. So, but for two-sided, you have to allow at least one here or add at least one, exactly one. You don't need to add two normal variables. Adding one is enough. And of course, we recall that Gaussian densities are also totally positive or Pólya frequency. So proving the individual atoms are totally non-negative is easy. Convolution is easy, and that's all there is. That's what Schoenberg is saying. And in the language of probability, it's literally, these are the only densities or random variables whose linear combinations give you totally non-negative density functions, frequency functions. Pólya frequency. Okay. And so general Pólya frequency functions are the same as above, up to some rescaling here and there. So this is the set of Pólya frequency functions, and this is the second part of my talk. So now let me see how much of this I can do. So I want to talk about the preservers of some of these things.
One word about the big groups
Yeah.
before that.
Before that. So yeah, so these also show up from the side of representation theory of the infinite unitary group, the infinite symmetric group, and what am I missing? Maybe that's it. Yeah. Sort of Schur-Weil dual groups. In some sense, yeah, from the characters of these guys, if you look at the characters of which representations, irreducible unitary
Yeah, infinite dimensional.
infinite dimensional unitary representations of these guys. The characters exactly reveal to you Pólya frequency functions. So this is how Gelfand and Olshansky, there's a big group. Yeah, exactly.
Vershik.
Vershik, exactly.
Yeah.
Thoma, that's true. Thomas theorem. Yeah, exactly. Oh, yeah, that's true. Thank you. Good. Well, we have more experts in the audience than me, which is even better. But yes. Thoma, Vaikulescu, Olshansky, Vershik, lots of people. Later, Okunkov also had something to do with it. Right? Or was that? Did we read a paper with Okunkov's name? Okunkov and Kirov or something.
Yeah.
So so that side of the picture is also there, which sadly did not touch upon at all. But that will itself probably take up, I don't know, 2 lectures, which Mihai will give the next time we have a conference here. Or you can tell us tomorrow. Okay. So finally, then I come to the notion of preservers. And there are some, at least I want to tell you a couple of interesting things. So we tried to understand, Alex, Dominique, Mihai, and I have been working on preservers of positive semi-definiteness for a long time, since we met at AIM 10 years ago when we first met. And since then, we have gone to positive eigenvalues and now negative eigenvalues, preserving them. This was we decided to look at in the same vein. What about if you apply some entry-wise transformations to matrices, which are totally positive? Or more generally, if you look at kernels, like Pólya frequency functions, they're kernels on R cross R, then we are saying that you have a function lambda, which is totally non-negative or totally positive. Okay, so you have a function lambda, which is totally positive or totally non-negative. Let's say totally positive, for example. And now I want to say, well, then F composed with lambda should be totally positive. This is the property that I want to characterize. And I want to therefore find all functions F taking 0 infinity to itself, such that this is the general problem in general for any two kernels. So this actually, maybe I should really give credit where it's due. It was not our problem. I was at Courant for some other reason in 2017, and I met Percy Deift, and I was describing some of these positivity preserver results to him. And he said, I'm interested in total positivity. What are the preservers there? And then he said, we haven't thought about this, and nobody had. So we looked at that. So let me describe a couple of settings to you. No, 3 or 4 settings to you. So let's start with 2 by 2 Tn matrix. Very simple case. This is the easiest case. So which functions? So let's say, look at matrices. So the kernels X and Y have size 2. So now this is like 1, 2. These are the rows and these are the columns, indexing the rows and columns. So then what you do is very simple. You take 2 clever choices of matrices. Let X and Y be non-negative. Look at A here and B here. The determinant, of course, is 0 for both of them. All the entries are non-negative. So these matrices are Ti. Now I want a function that acts entry-wise and preserves. So what happens when I act on A? I get f of xy, x f of x, f of xy, f of 1, f of 1. Again, f is going, let's say I want to do Tn. So I'll change this to Tn for now. So then I take closed 0. I allow for non-negative values. So I get this matrix. Clearly, if f takes all the entries must be non-negative. So f has to be of this kind. And the determinant is bigger equals 0. I get a functional inequality. If I apply that same function entry-wise here, I get exactly the same inequality, but reversed. Because now f of xy, f of 1 is bigger equals this. Here f of xy, f of 1 was less equals. So I therefore get equality. So if I denote g of x to be normalized, let's assume that f is non-zero. One can check what happens. Otherwise, you literally see that this equality means that g is multiplicative. and there are very few multiplicative functions. You know that also we know that G is multiplicative and measurable. It is non-decreasing. That's easy to prove. I can look at, for example, like x, x, y, y. X bigger equals y. Then f of x square is bigger than f of y square. So f of x is bigger than f of y. So f is non-decreasing and multiplicative, or G is, hence measurable. So, this analog of Cauchy's functional equation, but in the multiplicative setting with logs and exps or something, gives you that the only answers are power functions like this or the indicator function, Heaviside function. The converse is easy to prove. You're looking at 2 by 2 minors. If AD is bigger than BC and they're all non-negative, then you can raise it to any power and that still stays the same. That's just trivial. So that's why this. So 2 by 2 is easy, but for Tn. Now, but we wanted to answer for general kernels, general domains. So what happens if you have Tn kernels of order 2? So what do I mean by order 2? It just means that you look at submatrices of size 2 by 2 or smaller. So again, a kernel is Tn of order k if all minors of size less equals k are non-negative. And the answer is exactly the same. You either get a power function or a Heaviside function. And that's why is that? It's because if you take a big like x here and a big y here, I can still embed any 2 cross 2 matrix A, B, C, D anywhere I want and just pair it by zeros everywhere. This is still, if the original matrix is Tn, then this kernel is totally non-negative.
What do you mean? But one when x greater than your function is defined only on the positive semi-axis, no?
No. X is any totally ordered set.
F.
Yes. Yeah, I
Yeah.
know. Yeah, so I'm saying I'm looking at this here.
Yes, I understand. But
So lambda of xy is in 0 infinity.
0.
So f of lambda of xy is like f of ai. This is like aij. That's a real number.
no, I understand. But if you write f of x equals c 1 for x greater than 0, it included in this previous, because your function is.
Oh, I should point out, sorry.
Yes.
0 to the 0 is defined to be 1. So the 0th power is, so the 0th power I should have mentioned is this is the 0th power and this is the
Okay.
Heaviside function. So that they differ at the value at 0. That's right. But yeah, with just the 1 point difference, these are two different functions and they both work. And yeah, these are because basically, of course, each of these works and conversely you act by any preserver to after you pad it by 0. So then basically all of these give you, just working with the 2 by 2 matrices, which are valid kernels here, gives you that they are power functions or the Heaviside function. Okay, so but the interesting part was this one. Okay, good, I have time. What happens about TP? So now for TP is where I can take it back to what I had written. So these are now open intervals. This part is still fine. This setting 3 is still going to be fine. Setting 4 is where the problem happens. So first you show that f is increasing because you just apply it to this kind of a matrix. So f of x square is strictly bigger than f of y square because the determinant is strictly positive. Now show that using that one can show, it takes a little bit of work, but one can show using f of x plus, if you will, that f is continuous. And then therefore it extends to a continuous function. It's increasing, continuous and positive. So it has a lower limit at 0. So you extend it to 0. And let's call this f again. So it's an extended function. And now we have this density theorem of Whitney, which Prajesh mentioned, that the 2 by 2 TP matrices are dense in the 2 by 2 Tn matrices. So if you take any Tn matrix, you converge to it by a sequence of TP, f preserves total positivity. In the limit, f preserves total non-negativity. Oh, very good. I forgot the word Tn, sorry. It preserves 2 by 2 matrices. That is true. It takes a 2 by 2 matrix to a 2 by 2 matrix. But that doesn't really say much. It takes a 2 by 2 Tn matrix, totally non-negative matrix, to another such matrix. So f is as above. F is exactly of the power function or Heaviside function kind. F cannot be constant on any interval because then some determinant would vanish. So f is a power function. modulo a constant. Fine. So, and conversely, again, if this was strictly bigger, if AD was strictly bigger than BC, then any positive power retains the inequality. So, 2 by 2 preservers are fine. But now, remember what we did in the previous case. We started with the 2 by 2 for Tn and extended it to arbitrary kernels. We could do that because you can pad such a matrix by zeros. You can fill up the entire x cross y outside something with zeros. Now you can no longer do that in total positivity. You can't even say I can do A, B, C, D, and then 1, 1, 1, 1, because this determinant is 0. I can't even pad it by ones, for example. This is also not allowed. Padding by zeros is not allowed. What do we do then? So then one has to come up with some clever tricks, roughly. So can define TP of finite order for any kernels. What are the preservers? Meaning if you take arbitrary totally ordered sets x and y of size 2 at least, and you take any kernel that's totally positive, then so is this. The answer is, what we could prove is the answer is exactly the same. It's still a power function for a positive power. But we cannot use padding by zeros, we cannot use padding by ones, because this will be TP1, it won't be TP2. It's 2 cross 2 minus that. So what do you do? So here we try to understand the situation before we tried the preservers. I have two totally ordered sets. Let's talk about total positivity. Forget preservers. I have two totally ordered sets, x and y. Each has size at least 2. On that, I have a TP2 kernel. I want to preserve a non-empty class of functions. So let's say I have at least one such kernel. What can I say about the sets themselves? Forget the kernel. Can I say something about the sets? How big can they be? For example, for totally non-negative, I could, by Zorn's lemma, take any set, totally ordered by Zorn's lemma, take any set, totally ordered by Zorn's lemma, and put the constant 0 kernel. That's a totally non-negative kernel on any two totally ordered sets of any cardinality, for example. In the totally positive case, this is not possible. There is actually a constraint. If there exists TP2 or TP kernels in x cross y, they must be uncountable at most. In fact, we embed them into 0 infinity. That's the first lemma you need to prove, but this already tells you that general totally positive kernels don't exist. They can only exist on domains which are uncountable at the most. And you can actually embed them. And that lemma is one line, but you can see the paper. It's a very nice argument, but I won't tell you that right now. I don't think I have the time. Second, now, can you embed every 2 cross 2 matrix? Fine. So you know that the domains have to be small. I mean, real line. Right? Fine. I don't have a general x and a general y. I have something in 0 infinity. But now I want to use the same argument. I want to embed a TP matrix without padding by zeros or padding by ones into an actual kernel, into a TP2 kernel or a kernel. Then I can say that by the same argument of continuity and Whitney's density, I can do it. How do I embed a TP matrix into this? So now we have understood something about the domains. Now we understand something about the matrices, and then we will understand something about the preservers. So domains is done. They have to be between 0 and infinity. We can't pad by zeros, but still, yes, we can embed every 2 cross 2 TP matrix into a TP kernel of all orders, not just TP2 kernel, not just 2 by 2. We can embed it into a kernel where every square minor is positive. Why? And what is that minor? What is the kernel that we embed into? This is, I think, called Chekhov's gun, right? If you introduce a gun in the first act of the play, then you must shoot it in the last act of the play. The very first example that we started with in the talk was generalized van der Waals matrices. That is the kernel. Every 2 cross 2 TP matrix up to rescaling by a positive number is a generalized van der Waals matrix. Therefore, well, what do you embed on 0 infinity? This kernel. This is a generalized van der Waals. And now restrict to x cross y, you're done. Now we can adopt the same argument and finish the argument. Okay, and in fact, so in our paper, so this was just the 2 by 2, but already this requires a couple of new observations. One about the sizes of the domains, one about every 2 cross 2 TP matrix being van der Waals, and therefore embedding into a kernel on any such domain. So here we really needed the first observation, that the size of the domain is between 0 and 0 infinity, and therefore you can do this. And finally, in our paper, we do the full problem. So it's quite a long paper, and we do much more than just matrices and kernels. We do structured kernels, preservers. We classify the preservers for all integers k, including infinity, and all non-empty partially ordered sets. But now we know that the moment it's TP, these sets aren't arbitrary. They have to be in 0 infinity. That's a sort of a misleading all non-empty sets. It's inside 0 infinity. Right? We could also do things, as I said, just look at the title because I am out of time. But yeah, the theorem was that you can also preserve Pólya frequency sequences or one-sided ones. We did Pólya frequency functions, one-sided of those. We did totally non-negative function preservers. We did lots of different kinds of preservers in this one paper. So every chapter was every section was a new problem in the line of preserving total positivity. Okay, so these are the references. Pólya and Schur was the multiplier sequence result. Schoenberg introduced and classified the PF functions here. These were the two papers where they classified the PF sequences, one-sided, I guess, also two-sided maybe. Olga's result about the Riemann zeta, Karl Heinz's result about the Riemann zeta. This is the Hirschman-Widder density paper where we, and this is the last one where we classified the preservers. Okay, thank you so much. And thank you to all the speakers because I'm the last speaker of the day. That's it.